Good afternoon, everybody. How are you? Sorry. Oh, oops. Sorry, wrong camera. Yeah. Hold on. Hello. How are you? Hey, everybody. Jaslyn, Christian, Dean, Sebastian, Juliana, Devon, Isaac, Sorush, Ray, Alexia, Eleanor, Amelia. This is how I practice all your names. Evelyn, Feng, Carla with the K, Cameron with the C, Gauli. How are you guys doing?
Good.
Deal.
I found your identical twin.
That fan looks so comforting, Isaac, on top of your head. Hey, Christian. I can see your smiling face. Thanks for smiling. I see too many sad faces these days, especially with this cover. I can't tell. Are you happy? Are you making fun of me? Or are you actually happy and smiling?
Can you hear me?
Any news from anyone? Any updates of your life? You got a you got an alligator as a pet? I don't feel like teaching today. I don't know why. Should we just take a walk, a Zoom tour? I don't know what that is.
Professor, how long do we have on the quiz?
You have about 5 minutes to do like 50 questions. Not funny. That's how it's gonna be. Our store is laughing. Adele is laughing. Varun is thinking, shall I smile? I'm supposed to look very serious.
Dr. Maitri,
What's up?
I found your identical twin over the weekend.
You found whose twin?
Yours.
My twin?
Yeah, and know what's even weirder about it? He's
are you
he's-
kissing up to me before
no,
before the quiz?
he's a chemistry professor. It's so weird. I was just like I
Where
was
is he
looking.
at?
He's at UC Santa Barbara. I was looking through their chem department.
Oh man, I have
column.
to look.
Here, I can show. Yeah, look it
So,
up.
share your screen.
Okay, wait. I
Oh,
can't
I
share
have
my
to see
screen.
it.
Okay, hold on. Let me do this.
With long hair or short hair? Which one? I
He
have
has like short hair, but he has like he has like an afro. Hold up, let me show you.
That's really funny. Okay, you are distracting me. It's not my fault today. Okay, I know that I'm very easily distracted, but today it's a Christian's fault.
Yeah, I had to tell you this one. Okay, hold on.
Okay,
How?
there is something going on in the chat. Now I'm very curious. What were you guys writing? What? mail.fresnostate.edu. Do you know that I got off the syllabus only sent it to your. Yeah, that's my CSU Fresno email. What's wrong with that? I don't know what Alexia. Alexia, you can tell me. We can talk later on. Hi, Feng. Hi, Carla. Thanks for using the chat. That does look like me, man. This is like me, like 100 years ago. But he looks like he's high on something.
He looks high. Yeah, I was like,
what's his name?
wrong. I don't know. I just saw him.
I have to share it with my friends. Hold on.
Okay, yeah.
I'm not going to go through technology. I'm just going to take a snapshot of the of the screen. Hold on.
Okay.
His eyes are suspiciously red.
He's one of my students. You might know him, Michael. Yeah, he's here right now. Michael is looking for a PhD professor. Hold on. Can you put it back again?
Oh yeah, hold on.
Put it back, Christian. Man, you guys are talking about me and making fun of me on my back. I think everybody's gonna fail, okay? What's his name?
I don't know. Ram Seshard.
Seshadri. Yeah, he's an Indian dude. He doesn't have gray hair, so he's at least 40 years younger than me.
Mhm.
And he's from India.
I think he's painting it.
He's
think
what?
He's dyeing his hair.
Could he be my twin brother who was separated at birth?
He could be, to be honest.
Okay, are you guys like deliberately distracting me so that you guys don't we learn less material for the next exam? You know, come on, man. I have been there, done that, right? Okay, I'm not proud of my past. So I've done some bad things in my youngerhood. I still do bad things. It's good that, you know, unless you screw up, you don't evolve. Just imagine if you're just a good person, 4.0 GPA in GPA, like how are you going to evolve unless you slip and fall? So slipping and falling and making mistakes and saying, "Oh my God, I'm so sorry. I will never do that. I'll never throw rocks at the." Never mind. Never mind. I shouldn't have started that sentence.
So then I should be your model student.
Who is saying that? Sorush?
I,
Okay, don't push me now, Sarush. Okay, okay, but at some point you need to kind of like realize your destiny and try to change your destiny. And I had that realization after undergraduate. Yeah. Okay, no more revealing my secrets. Okay, some every human being has a right to have some secrets deep down in their hearts. Yeah. Don't get into the dark zone. Okay, so today we are going to talk about. Oh, we have to finish that epoxide synthesis. I was so excited to talk about NMR. Okay, let's go to the board. Let's see what we did for Chem 128A. Does it look like gibberish? This is not science. This is not chemistry. Who knows what I was talking about? I was talking about that stereochemistry. Okay, I need to erase the board. Let's go. The quiz is not a free response quiz. It's a multiple choice quiz. Okay, it's off of Canvas. So it's going to open up. It's going to be available at 4:25 p.m. today. So in about an hour, and it's going to be available for 20 minutes. Okay, no books should be opened. You can have, you know, I know that some of you will not listen to me and some of your moral values may be still compromised even at this age. So if you do that, it's probably going to be, you're going to be digging your grave even deeper. So there are about 8 questions, no bonus questions. There was a bonus question for Chem 128A, but that's kindergarten 1 and you guys are in kindergarten 2+. So you guys don't get such deals. You guys are like more like pro right now. So you don't need bonus points. So the 8 questions, each question is 3 points, 24 points. Multiple choice, you can look at the other questions because you will have to look at sometimes like question 1 and question 2 and 3 and 4 might follow question 1. You may still have to look at that the molecules and scheme, but it's like choosing one of the 4 answers. It's pretty straightforward if you know the answer, if you know what is going on. And if you're scrambling for your answer, or if you're talking to your friend for an answer, you're probably going to be dragging yourself down. So you have 2.5 minutes to answer each question. So if you're too delayed, you might be making mistakes. So I want to see like how it goes. That this doesn't guarantee that the upcoming exam and the last quiz and the final exam are going to be Canvas multiple choice. It's probably not going to be multiple choice. It's going to be a free response. So don't get too excited. Okay, this is just a short time break for you and for me and the rest of the world. Not rest of the world, just you guys and me. Okay, so we're going to talk about that epoxide synthesis. If I remember that mechanism correctly, it's just a little tricky how you organize the molecule. If you don't, if I don't remember how to organize that molecule, you will see me fumbling. Okay, hopefully I will not do that. I haven't prepared for that mechanism, so hopefully I'll pull it off. So we are not Chem 128A, we are Chem 128B. So can somebody, if I forget, which will happen or may not happen, around 4:20, I think I should let you guys go. We should probably hang up latest by 4:23 p.m. I want you guys to have like 2 minutes to kind of put yourself together and go to Canvas and make sure Wi-Fi is working and things like that. There have been several emails from my 128A students that, oh, my Wi-Fi was not working, oh, something happened, something else happened, some complaints like why they couldn't turn it in on time. So time is very important. I'm not going to be showering with mercy or compassion if you haven't been able to finish it on time. So that's your problem. So if you are looking in the book, you will not finish. Okay, just do the math. 8 questions, 20 minutes. Okay, so we are going to finish this today, and we're going to start talking about NMR today too. I promise. It's a promise. I'm going to keep that promise, unlike in the past. Okay, so sorry about this. I should have cleaned it up earlier, but today has been a little hectic day. Now that picture is going to be bothering me for the rest of the day, Christian. It's all your fault. If I'm distracted, you know who to blame. It's not me. It's Christian. Christian, are you looking at PhD after this? What's your deal?
Oh no, I just used to go there, so I don't know. I was just browsing through it.
Are you there, Michael?
Yeah, I had to join from my desktop today. My laptop's doing some weird
that's
stuff.
fine. Michael, you don't remember? Christian, that was UCSB or UCSD? Which school was it? The
It was
materials
UCSB. I know. I remember seeing that guy's lab.
Okay.
Actually, one of my lab professors there was from Fresno State, ironically.
Okay. All right, so 128B, today is March 23rd. And we are still talking about ethers. Under ether, cyclic ether. And under cyclic ether, we are talking about epoxide. The smallest of the bunch, okay? It's this guy. That's the cyclic ether that's possible. Why they're important? Because they're unstable, because it likes to open up. That's why they're lucrative for synthetic people, okay? The synthetic chemists like to make epoxides, but because now you can use other nucleophiles to open it up, okay? All the list of nucleophiles that we have gone through, they all are applicable to opening this up. So right now we are discussing how to make the cyclic ether, how to make an epoxide. Okay, that's kind of like our goal today. So ethers, cyclic ethers, and epoxides. Okay, so we were discussing how to make a cyclic ether. Okay. So what I'm going to do is I'm going to make this guy. It's not really straight. Okay. Realize that an epoxide can be of different kinds. It's not just that. Okay, because an epoxide can have, there's a carbon here, and there's a carbon here, and if this molecule, you can appreciate that. When you have a cyclic, when you have a this is of no use. Okay, well, that's your oxygen. Let's say that's your oxygen, and hopefully I won't break it. Okay, you know that. So that's your oxygen. These are the lone pairs, and this is your cyclus. I have broken one already. Okay, that's your epoxide. You can see that strain, right? The angle, they're all in sp3 hybridization. They're all sp3. sp3, sp3, and sp3. Okay. The problem is it's got a lot of ring strain because the angles are 90 degrees. This is better than cyclopropane. Cyclopropane, the carbon-carbon bond is shorter. Oxygen and carbon bond is a little bit longer, so it gives it little room to flex. So the bond strain is little less. However, this bond is little sketchy. Okay, that bond and that bond. This bond is pretty solid. It's a solid bond. Strong. Relative scale. This is weak. This is also weak. Okay, these two bonds are weak. Carbon-oxygen bond is weak because the electrons are pulled in this direction due to electronegativity, and the bonds are pretty polarized. So there is a possibility that if you could hit the right corner with the right species, this bond might open up, okay, this way. There is a chance that the electrons might, the bond can break here. So that's the vulnerability of this molecule, and that's why it's lucrative. Because if you could make that compound, and if you could keep it stable for some time, you can do magic with epoxides. You can do all kinds of really cool reactions. Realize that these are the lone pairs. This is green. These are the lone pairs. But you can have, I'm just going to put different things here. So you can have 4 hydrogens down here. You can have 2 hydrogens on this side and 2 hydrogens on that side. That's the smallest epoxide. You could have a methyl group here and a methyl group here, right? So you can have an epoxide with 2 methyl groups and 2 hydrogens. Now things are getting really interesting right now. Now the molecule could be both methyl groups down, or it could be 1 methyl group out from the left side and 1 methyl group behind from the right side. Now you can tell this is going to be more interesting because if you take its mirror image, let's make a mirror image. Let's do some what am I talking about? Let's do some stereochemistry because I was working on stereochemistry in the previous class. Okay. I don't want to break it. Who can predict? Who can predict this molecule? Okay, the methyl group out and methyl group in, up and down. Left one is up, right one is down. This molecule or this molecule, which one will be not superimposable on its mirror image? This guy or this guy? This is A, this is like an eye exam. Can you see it better with this lens or this lens? 2 methyls down or this one? So let's say this is number 1, this is number 2. That's 1, that's 2. Which one will be not superimposable on its mirror image? Who can tell? This is 1, this is 2. That's 2. This is 1. I should have been an ophthalmologist's assistant. I think I'll shine in that job. This is 1 and this is the other one is 2. Which one will be not superimposable? Which one will be an enantiomer with its mirror image? This guy or the previous guy?
That one.
This one, then, or the previous one? I can't hear you. Unmute yourself.
Not that one.
Not this one.
Not this one, the other one.
Other one? Okay. What do you guys think? Don't you think that once you turn it, it becomes the same molecule? No? I can't fool you?
I mean, if you turn it, yes, but not if you like mirror it.
Okay, so its mirror image would look like this. It's going to be difficult for me to fold it, so let's see. So these are the mirror images, right? That they look like mirror image, right? Do you guys agree that I built the model properly?
Yes.
They're mirror images
Yes.
from whatever angle you see, right? They're mirror images. They're mirror images, right? So now, since we have established that they're mirror images, let's try to superimpose. Well. They don't superimpose. Let's try to turn it. Well. They still don't superimpose. So yes, so two epoxides can be enantiomers like this. So even if you have the same group on both sides, okay, hydrogen and methyl, when they're down and up, and when it's up and down, they're enantiomers. It's pretty cool. Now let's check out the other guy. Okay, mirror image. You can tell, most of you who can see things with your eyes closed, they're superimposable, right? So there is a name for this guy, even though it has two chiral center. That's a chiral center, that's a chiral center. Why is it a chiral center? Well, hydrogen, right? You have to have four different things attached to itself. That's a hydrogen, that's a methyl, that's something weird, like another group, and this carbon is attached to this group. That's oxygen, right? So oxygen with two lone pairs. And this is a CH with a methyl group. That's just a methyl group, that's a hydrogen. So that's a chiral center. This is also a chiral center, but it's superimposable on its mirror image, even though it has two chiral centers. What are those compounds called? It's a four-letter word. The last letter is O. I'm not going to tell you the first letter. What is that called? You learned it in 128A. In one of the Star Wars movies, that strange character who was hated by almost everybody, I thought he was funny, Jar Jar Binks. He used to use almost that word with a different letter at the end.
Meso compound?
Sorry?
Meso compound?
Meso compounds. There you go. Thank you, Benita. Appreciate it. That's called meso compound. So if you have forgotten, study, because it's fair game for me. Okay. So the way I'm going to draw this molecule is I'm going to draw it this way. I'm going to say R1, R2, R3, and R4. Okay. So R1, R2, R3, and R4 could be hydrogens. When it's just simple, the smallest epoxide. R1 can be methyl, R4 can be methyl, R2 and R3 can be hydrogens. So that's how when you write a publication, you don't draw like every darn compound, like 120 compounds in your manuscript. Sometimes you use a formula and you say, well, R1, R2, R3, R4 can be hydrogen, can be methyl, can be ethyl, can be chloro, can be bromo, can be nitro, can be this, and can be that, whatever. That tells the story. So the reviewer and the audience knows like what kind of compounds you have dealt with. Then you highlight the ones that are the front runners, are the lead compounds, or the famous compounds, the star molecules. Okay. Let's go back to our, distraction. All Christians' fault. It's not my fault today. 3:52. We still have some time. Let's at least go through the chemistry. Okay. So now what I'm going to do is I'm going to draw this starting compound we're using R1, R2, R3, R4. Okay. I'm going to draw this alkene R1, R2, R3, R4. You can also draw the same molecule in a slightly different way. I don't like it, but sometimes it's useful. Sometimes I'm forced to do it this way. It's not wrong. It's not wrong, but I personally like to draw this way. Okay, it's the same thing. Same thing, but looking from the side and looking from the top. Okay. Maybe I should just move this guy. I'm not going to delete it, but then I'm going to move it to the corner because that's our destination. Okay, that's where we are going. Okay, so we start with this molecule and we react it with. Now this is where I have to remember exactly so that I don't look like a total idiot in front of you guys. NCPBA. I'm going to draw that molecule in colors. Metachloroperbenzoic acid. So let's put that metachloro in metachloroperbenzoic acid. Let's make the benzene ring that color and acid this color. Okay, and this molecule looks like this. We will be talking about aromatic compounds after we finish NMR. That's benzene. Okay. This would have been benzoic acid. It's not, it's benzoic acid. So one more oxygen. This is the oxygen, and that's benzoic acid. You know what? I think now I remember how to draw this guy. That's the benzoic acid, and meta position means it's something that we're going to be learning in aromatic chemistry. Meta position means not next door, but the next door. That's the meta. Okay. This would have been, this position is called ortho. That's ortho. That's meta. One door away. And the last location is called para. That's para. Okay. Metachloro. There is a chlorine there. So this is the molecule. That's metachloroperbenzoic acid. Metachloroperbenzoic acid. Okay, that's MCPBA. So MCPBA reacts with this one and forms R1, R2, R3, and R4. Either that or this. R3, R4, R1, R2, down here. Okay, I'll explain what's going on. Either this and this, and it's usually 50% of that and 50% of this. And what's the relationship? What if we call this molecules molecule A and molecule B? What is the relationship? What is A and B? What is the relationship? They're friends, they're twin brothers, they're non-identical twin brothers, they're husband, wife, they're father and daughter. What is the relationship? They're meso. What's going on here? Or that's a ridiculous question. Think carefully while I try to pull up that mechanism. Think about it. Okay. So I need some space. Please let me remember how it works. It's a little tricky. Once you align the molecule, then it's pretty easy. Okay. Let's put the pi bond in red color. I need to move this guy out somewhere else. So it's the same compound as this. R1, R2, R3, and R4. The same molecule as this guy. Okay. And then we have the rest of the compound. Aromatic ring, and then there is a chlorine, the meta position. It doesn't matter whether I draw the chlorine here or here. The mechanism, the way it works is the following. I remember that the pi bond grabs that. Okay. This moves down here. This bond grabs that hydrogen, oxygen, and that bond moves down here. Yes, I got it. I didn't look like a complete idiot, maybe half idiot, because I was a little hesitant. Okay. Let me just clean up this part a little bit. Okay. So the double bond, the way you draw, the trick is how you position that MCPBA guy, okay, with that extra oxygen. Remember this, put that extra oxygen very close to that double bond. Put the hydrogen kind of like a V. Put the hydrogen up here on one side, it doesn't matter left or right, and then draw that oxygen, the normal oxygen of the carboxylic acid, and keep that double bonded carbonyl oxygen in that like an invisible loop. Don't put it the other way, then you are screwed, okay? If you put that oxygen here and the benzene ring here, you can't pull it off, okay? I have done it in the past. So put the oxygen here. The whole idea is that double bonded oxygen, the carbonyl oxygen, grabs the proton because you want to make benzoic acid from here. You are just dropping that extra oxygen because it's a strong oxidant. You need to drop that purple oxygen. Okay, that's the whole idea. If you can kind of like, I'm horrible with directions, but if my wife and our son says that if dad at least makes an effort to think about the destination and how he can do it, he can pull it off. He just doesn't do it because now we have the invention of the GPS. So that has really crippled me. There is a saying in our language that when you see a horse, you feel that your legs are paining. You don't want to walk. Okay, it's kind of like that. So the double bond grabs the proton. If it is grabbing the proton, then this bond has to go somewhere. Now realize that this bond has to make a brand new bond for the brand new epoxide. Okay, and the pi bond is going to be gone. So the pi bond has to reach back to make that second bond to that oxygen. One bond is that bond, the purple bond. The other bond is the X pi bond. And this bond has to completely detach itself from between that oxygens. And that goes back there to make that carbonyl, the brand new carbonyl, okay? And let's see how it looks like. So now we have R2. The red bond is up. the purple oxygen is down, and the purple bond is the second bond down here. And what else has happened? Well, during this process, what you have produced also is, I'm going to draw it in the same orientation. The chlorine up, and that's the new carbonyl. That's the new C double bond oxygen. And that's the X, the old carbonyl. It's now a single bond. But what did it get? What did it lose? It lost the pi double bond, but it has a brand new bond now. That's how it happens. Now realize that this molecule, the way I have drawn it like this. I'm using this Amazon packet as a model. So if I draw the molecule R1, I have something inside actually. R2, R3, and R4, right? So that's the molecule. R1, R2, R3, R4, but I'm holding it this way, kind of like slanted. Okay. And the oxygen, what do I use as an oxygen? Just imagine that this is the oxygen. Imagine that's the oxygen. It's this little cap for my purple pen. Purple rain. Purple, it's raining from the top. That's the purple rain. Raindrop, purple raindrop. The purple raindrop is attaching itself from the top. And this is how the molecule looks like. That everything is there, the double bond is gone, and the epoxide is made on the top. But what's wrong with the bottom side? Bottom side and the top side are pretty much the same, right? So the epoxide, the MCPBA, that big molecule, can approach it from the top or from the bottom. So if it approached it from the bottom, what would happen? Well, you know what would happen. It's if I wish I had one more finger, two more fingers. I want odd number of fingers. Don't ask me why. So you can make that molecule, or R3, R4, R1, R2, and down here, the oxygen could be attached at the bottom. Okay, and the same thing would happen here. So you're going to make 50% of this guy and 50% of that guy. So MCPBA works perfectly for making an epoxide from a double bond. It's one of the most trouble-free reactions that it doesn't have its own mind. It will work. If something goes wrong with this reaction, it's me or you to be blamed. Okay, this is a really fantastic reaction. It goes with very high yield. So MCPBA reaction and the mechanism is included for the next test. Okay, take a look at it. I'm going to take a picture, and I don't know what I'm going to do right now. What time is it now? 4:06. We still have some time. Maybe we should get started with NMR. Let's take a picture. It's pretty hot in my office right now. Really hot. Take a look at the mechanism. This mechanism is important. If you learn it, if you practice it, you can pull it off. It's not. It's just trick, learning some trick. You need to practice it. It's not going to be enough practice if you just watch me do it. Remember that I was a little nervous about pulling it off. I could have made a mistake if I drew it wrong. Okay. And it is important to know that if you start with a chiral molecule or not chiral molecule, the resulting molecule might be chiral. So you should probably revisit your stereochemistry chapter and just your old notes and stuff, because I might ask you some questions about chirality related to the epoxide. We need to do something I completely forgot. Reactions of epoxides, okay? Unfortunately. So this is synthesis of epoxide. There is another synthesis of epoxide. I think I'm going to skip it. I'm going to cut you guys some slack. Yeah, it's not important. Just know that epoxides can be made using MCPBA. There is actually a gentleman who used to be at MIT, Barry Sharpless. There is a funny story about one of his eyes. He lost his eye vision sharpness. His name is Sharpless. People started cracking jokes after an NMR tube exploded and he lost one of his eyes. So people started saying he's actually really sharpless now. His eyesight has lost its sharpness. But that was a mean joke. I never said anything like that. So he was famous for, he got Nobel Prize for making one epoxide over the other using some chiral catalyst. Very cool, very cool chemistry. So if you Google Sharpless oxidation, it'll pop out like what exactly he uses. He uses some titanium salts, titanium molecules, the organometallic compounds, and it has some stereochemistry involved with it, like broken symmetry. It has lack of symmetry, the catalyst, and the catalyst binds with one side of the molecule of the double bond and allows the oxygen to be dropped exclusively from, or more primarily from one side, not the other. That's called asymmetric synthesis. When you can make left hand or right hand, but you end up making more of right hand because you're using somebody else's right hand to block this hand. Okay, my right hand shakes hand with your right hand, right? If you stretch your right hand, right, you're going to be blocking my right hand. My left hand will be more free. So that's the whole idea. And if your right hand is acting like a catalyst to only make my left hand work because I'm better with my left hand. So you stretch your right hand. I shake your right hand with my right hand. My right hand is blocked. Now my left hand can do the business. Okay, and that's how chiral, like asymmetric synthesis happens. Your right hand is the catalyst, and it's blocking my right hand. Otherwise, I would have done the job 50% with my right hand and 50% with my left hand. I'm using from your perspective. This is your left side. So even though it's my right hand, I'm calling it my left hand. Okay, I'm not that crazy yet. Not that mental state yet. Maybe another 5 years. Give me 5 years, it'll probably lose track of the sides. Okay. Let's talk about some chemistry. So this is the only synthesis of epoxide. I took a picture. Let's talk about some chemistry. And I'm going to skip probably some part of it. I'm just going to say that all the nucleophiles that you can think about can work with an epoxide to open them up. Okay, because it's a pretty strained ring, and that's what chemists take advantage of. Because if it were stable, it wouldn't react. Because it's unstable, it will react with the right conditions, under the right conditions with the right reagent. That's the whole idea. So now let's look at how you can open up an epoxide. Okay, I'm going to keep the epoxide simple. I'm not going to draw the R1, R2, R3, R4, all that stuff. I'm just going to keep it very simple. But the problems that you might encounter might be less simple, maybe a little more complex than what you see here today. So be prepared for some challenges in the future. I promise that it's not going to be everything in the next exam, but maybe one question will be a little complicated. Maybe you will have to think and answer. Okay. So when you have an epoxide, let's say you have an epoxide. Let's say this is your epoxide. So now we are talking about epoxide reaction. Okay, we're talking about epoxide reaction. I don't think this color looks really prominent. So let's say we have an epoxide, a simple epoxide. Okay. And let me just write down CH2. I'm just drawing it in 2D. I don't want to complicate things right now. Just keep it simple. Then we can worry about the stereochemistry later on. Let's say we just have a simple epoxide, and it's reacting it with you're reacting it with a nucleophile. Okay, we'll use a specific nucleophile. Let's use this epoxide. So this is the generic epoxide, I mean nucleophile. Let's use a specific nucleophile. How about sodium ethoxide? So we use this guy. This is called sodium epoxide. How can you make this sodium epoxide on the side? Well, you use your favorite alcohol, and you can actually put sodium in there. You can make that, but sodium and alcohol will be you can actually do it that way, but I think a more sane way to make it will be to use something called sodium hydride. Okay, this is called sodium hydride. It's a pretty reactive species. If you put water, it can catch fire. So it will form sodium ethoxide and hydrogen gas. Hydrogen gas, whenever you show an arrow going up, that means you're producing it as a gas. It's going to escape the reaction or stay dissolved or something like that. It'll probably escape. So this is on the side. That's how you make sodium ethoxide. So if you react an epoxide with sodium ethoxide, let's change the color of this guy. Let's use a different color so that the parts can be seen. Green oxygen and a black molecule with black hydrogens. What do you think? How will I show the first mechanistic arrow to show like what's happening, who is attacking who? Do you see in this molecule, even though we have two lone pairs, okay? That's kind of nucleophilic. Do you see the strongest nucleophilic center between this molecule and that molecule? Which part will be the strongest nucleophilic center? Like ready to attack something.
Ethoxide.
Ethoxide what? Here?
No, the oxygen.
Here? I'm just distracted.
No, on the oxygen.
If I ask you a question, if I ask you a really dumb question, 415. Sorry, I should use this language. How many lone pairs does this purple oxygen have? Don't answer, so let someone else answer. I want to hear a wrong answer so that I can mock you. How many lone pairs does this purple oxygen have? Something is wrong. I don't know what's inside the coffee. I'm not feeling like normal person.
3.
3? Are you crazy, Sebastian? Who thinks he's crazy or who thinks he's normal? I'm crazy. How many lone pairs does this purple oxygen have? That could be a bonus question for minus 0.1 points. How many lone pairs does the purple oxygen have? I want to hear from 2 more people. 2 more students.
I
What?
agree with you, and there's 3 lone pairs.
3 lone pairs? Okay, 3 lone pairs. Okay, whatever. Okay, so that's the most nucleophilic center. What do you think will happen? Where do I start the first mechanistic arrow and where do I terminate that arrow? Who hits whom? This lone pair attacks the sodium. This carbon CH attacks, I don't know, it cannot bite its own tail. Too bad. What do you think will happen? Who will attack whom? Electron, organic chemistry, electron flow. More electron center to less electron center. Where should the arrow begin? Where is maximum amount of electron density? Tell me that.
It should begin on the negative oxygen.
Okay, so it starts here. And what does it, which part of the epoxide is most vulnerable to nucleophilic attack? Where does this arrow end? Does it pick up a hydrogen from here? Does it attack the oxygen or does it attack one of the two carbons? What do you think? Think about the product. If I take the dirt road, do I take my Prius into the ocean? Is that a good thing to do? If I pull the hydrogen, what happens? Well, this 2 electrons are here, it will become a C minus. Does it get me anywhere? Can that C minus fall down here and make a double bond between oxygen and carbon? Does it make sense from your past experience? Probably not. Should it attack? So attacking the hydrogen doesn't sound like a great idea to me. If it attacks an oxygen, that's also nucleophilic. Should one nucleophile hit another nucleophile? I don't think so. Then what's my third choice?
One of the carbons.
Carbon, okay. So if it attacks a carbon, carbon is not pentavalent. There was a time when I was in college, like you guys, and I was joking in the class, like, what if carbon turns out to be a pentavalent element? What will happen to all the chemists? They will just lose their job overnight. And somebody started giggling and we got into trouble. This is like, I was just in yours. It feels like yesterday, okay? So carbon is not pentavalent. So in order for carbon to stay tetravalent, just 4 bonds, some bond has to break. Which bond would that be? Come on, talk to me. I'm very lonely. I talk to myself all the time.
The carbon-oxygen bond?
Sure. So that bond breaks and goes here, right? Okay, let's see what's going on here. Where are we with time? 4:19. Okay, I need to call it a day pretty soon. So the epoxide is like this. There are 2 hydrogens. This dude is now stuck here with the little thingy, and then the oxygen is here with a negative charge. Looks good to me. So if you start this reaction, see, I put 1 in parentheses. This is not how the reaction is going to end. You cannot end a reaction with a negatively charged species unless you really want it that way. This is very unstable. What do you think we can do to make that green oxygen, negatively charged oxygen, neutral? What can we add to it? Something very simple, something very cheap. You even use it in cleaning your bathroom. What can you do? What can you provide this oxygen to just end its pain and make it neutral again? Simple, something simple. That species is called, starts with an A, the letter A. What is it?
Acetone.
Sorry?
Acetone.
Acetone? No. It looks like this. You need to distract this guy.
Would you be like an alpha halide? Halide?
That's a good idea. So you're using that as a nucleophile. Something not that complicated, Hannah. Something simple. It's like this is like a base right now, and this base is going to just pluck something. What are bases fond of plucking?
Acids.
Acids. So tell me something. The name of an acid that you have used to clean your bathroom or something.
Ammonia.
Ammonia is not an acid.
I think you could use
I once called an acid a base when I was drunk after drinking 3 beer in a group meeting because I didn't have any meal that whole day. I was a graduate student. And I was struggling to solve a problem, and my boss said, "What is an HF?" I said, "HF is a base." You sound very, very drunk to me. Okay. HCl. Come on, guys.
But isn't that like kind of like you use that one in the laboratory? That one always like has had like danger signs all over that one.
Ammonia is a base. If you say ammonia is an acid,
So I think it's a weak base.
that's why it's a base. Electron pair donor. We are 423. We need to cut it very quickly. Okay. So this guy plugs the proton, and I need to hurry up because otherwise you will be blaming me for taking up all your time. That's the product. So this is part 2. Part 2, part 1, part 2. This reaction has 2 steps. Okay. So we're going to continue with maybe one more reaction on epoxide on Thursday, and then we're going to start talking about NMR. Hang up and go to Canvas and take the quiz. Okay. It should be a pretty straightforward quiz. Good luck to you guys. I'll upload everything whenever I can. Good luck.
Professor, you said hang up. I thought we had to stay on here.
No, we don't have to stay. You don't have to keep your cameras on. Hold on for a second. Yeah.
So we should just log
Yeah,
on.
just go to Canvas. There's a multiple choice quiz. Take the quiz, and you don't have to. Just don't open book. Don't open the web. I trust you, so please reciprocate the right way. 20 minutes to do 8 questions. So I recommend that you just focus on the quiz and not get distracted. Okay. Bye. I'm going to read your chats. Hang up. Hang up. You don't waste your time with me. You have 1 minute to get to the quiz. You have 20 minutes. Don't waste your time.
May I talk to you for a moment?
Right now?
Yeah.
Do you want to take the quiz?
Well, I had a question actually about the quiz.
Okay.
I sent you an email earlier. My grandfather just recently passed away.
Yeah, you told me about that. I have. It's been a kind of hectic day.
So did you get my email?
I did read your email, but I didn't have the peace of mind to answer. So what were you asking me, Alexia?
I was just asking if I could take the quiz at a later date, but I understand if I can't.
You take care of yourself. If you cannot take the quiz, you cannot take the quiz. I think the best thing to do would be to give you the average of the 2 other quizzes. Okay.
And just not take this one at all?
I guess if you are not in a position to take it, you are here, you can still take it. But if you cannot take it, then I would recommend that I'll give you an average. I don't think I'm going to give you a makeup quiz right now.
Okay. I'll just take the quiz and see how I do.
Okay. Okay. All right.
Thank you.
Bye. Hannah, do you have? Okay. Yeah.
You want us to leave? Sorry, I didn't realize that. For some reason, I'm confused that we were supposed to stay on.
No, you don't have to stay on. Just take the quiz. You don't waste your time. You already lost a minute.
All right, bye.
Hang up. Bye.